Welcome to distributions. So distributions essentially are just different kind of histograms, but they're called distributions. So our I can statement for today is going to be that I can analyze and identify distributions. Okay, well, so as I mentioned, they're essentially are just different kind of histograms, because a histogram shows you how much of the data is in what location. So like this first one, this is going to be called a symmetric distribution, and obviously because it's symmetrical. But a majority of the information is kind of right in the center. And that's actually what a lot of distributions are going to look like, which we'll talk about in a minute. Um, but they don't have to look like this. They can look different. So like example 2 over here is that obviously two different kind of things are going on. And then that's just essentially also going to be called a symmetric one because it's symmetric down the middle. But not all of histograms and distributions are going to be symmetrical. So the non-symmetric histogram below shows that the data seems to be kind of one-sided. And for this example, it's about the mean heights of students. And you can see that there's, a lot of the data is just kind of over here. Well, and that's because there's apparently a lot of students that are all right about that same height in centimeters. And so it's clustered around that height. It's not symmetrical, and that's okay. But this is going to be called a skewed distribution. And the weird part is it's the exact opposite of what you're expecting. So over here on the side it says, is the height of the students skewed right or skewed left? How do you know? This is actually going to be called skewed left. And that's because instead of the left-hand side making it symmetrical, kind of like this, what happened is the left-hand side was kind of stretched out. And this will just be called skewed left. This tells you a lot of the height of students are, there's a lot of range of students' heights on the bottom half, and on the top half it's all kind of centered towards the same heights. Now, distributions and histograms are kind of interchangeable. The main difference is that histograms are, they go by intervals, and so you kind of have rectangles, you have blocks, where a distribution is smooth lines. And these are going to be the definitions of left skewed, which is kind of the example we had above, and a left skewed distribution is when the mode is the farthest to the right, the median, and then the mean is to the left of all of it. And right skewed is the exact opposite. And these are just going to be called skewed distributions, where a lot of the information is clustered on one side or the other. Now, a normal distribution is probably the most commonly used information, and especially for you as a student, because it's called the bell curve. And that might have been where you've heard it before. And the reason as a student it's common for you is because this is traditionally how grades are a lot of times calculated. So a normal distribution has everything kind of here in the middle. And this would be a majority of all of the information is right in the middle. And then it is kind of spread out to the right and left evenly, and goes down in quantity. Let me erase that. Okay. So, a couple things about normal distributions is it's actually often used for probability. And so, probability-wise, if you look at the entire graph, this would be 100% of the data. And so this would have a probability of 1. and we'll look at other questions where we're going to talk about probability or percents separately. But when I mentioned the middle, the mean is also like the mode, and it's symmetrical. Now, what happens with a normal distribution is they're broken up percentage-wise like this. These dotted lines are represented by standard deviations. So if this is the mean, if this is the mean, one standard deviation would be right here. And 34.1% of the information lies within one standard deviation. And if I go one more standard deviation to the right, 13.6% of the information lies there. One more, 2.2% of the information lies there. And then everything past this is going to be outliers, but it's also very little of the information, so essentially 0.1% of the info. And it's the exact opposite on the bottom half of the mean, but this is how the normal distributions are broken up. So let's get down to an example. It says the following curve shows the scores for the SAT, which is designed to be normally distributed with a mean of 500 and a standard deviation of 100. So this graph right here, it says what percent of the scores are between 400 and 600 on the SAT? Well, 500 is the mean and 100 is the standard deviation. So 100 to the left would be 400, 100 to the right would be 600. Each half of this shaded area is 34.1% of the data. So however you want to write it, it's 34.1%, 34.1% on each side. And if we want to know what percent of the scores are between 400 and 600, we're going to add them up. So we would have 68.2% of the data within one standard deviation on either side. So a majority of all the students will get this score. Okay, what is the probability that a score is above 600? So that's usually the students that do really well. Well, let me scroll down a little bit. So above 600 would be right here. From 500 to 600 was one standard deviation, which was 34.1%. 600 to 700 was one more standard deviation, which this is going to be 13.6%. I'll just start writing it over here, I guess. One standard deviation more would give you to 800, and that's going to be 2.2%. Now, traditionally, this is a lot of times where people stop, but it is possible that people are going to get scores above 800. Very few people, but if you get an above 800, that's going to be 0.1%. Add all of these up, you get 15.9%. Oh, I'm sorry, this is 2.2. 15.9%. Okay, different question from standard deviations. What is the probability that a score is less than 300 or greater than 700? Well, let's start off with the fact, I know you're not going to like heading back to probability from beginning of chapter 11, but that's pretty much what this is. Oh my goodness, now that I said the word probability, I realized what I botched up above. Question A was asking me for percentage. Question B was asking me for probability, and we often did answer probabilities with percentages, but traditionally on distributions, probabilities are answered as decimals instead. So I wouldn't have answered 15.9%, I would have answered 0.159, which honestly is the same information, but just written differently. So I'm sorry, back to C. Probability that a score is less than 300, greater than 700. Now in probabilities, this word or was kind of a big deal. And if we're trying to find the probability of one thing or another, that essentially means that we are going to add their probabilities together. So I'm going to do the two pieces separately and then add them. So probability less than 300. Well, I know that 2.2% of students land in this section, and I know that 0.1% of students are passed here, which follows the exact same on the other side. 2.2% of the students from here to here, 0.1 passed. So the probability the score is less than 300, well, that's 2.3%. Probability the score is greater than 700, also 2.3%. And the OR statement means that we are going to add them together, and that would give you 4.6%. But since we're trying to answer this as a probability for distributions, we're going to answer it as a decimal. So it will be 0.046. And we don't have a picture for D. We're just going to kind of go from that. What is the probability that a score is greater than 300? So if I use this picture from up above, why don't I pick a different color here? If I use this picture from up above, well, greater than 300 would be everything over here. And this entire picture is 100% of the information, or 1.0 for probability. If I'm asked to find this answer, but on the last question I found that answer, I can use that to find this. So what I'm going to do is I'm going to take 100% of the data, or 1 in probability, and I'm going to subtract this answer that I found previously, which was 2.3%. So I'm not writing them as percents, I'm writing as decimals. So 1 minus 0.023, and I would get an answer of 0.977. So that'd be 97.7%, or as a decimal, 0.977. Excellent. That's it for distributions.